So it came to my attention, much to my horror, that I didn't finish something that I wanted to finish for you guys for. And so so this will be useful on the homework. You don't actually need this on the homework, but I want to point out where it might be helpful. So I'm going to take like this is back to before my recorded lecture before I went to Fargo. I didn't finish up something that I wanted to finish up. So let me give you this. This first one's kind of a technical theorem here. And I'm going to be careful about how we decompose these ideals. We'll say that F over K is a finite extension. Number of fields. With R inside T, respective range of alpha integers. We'll also assume F is K alpha. With alpha and T. So actually any extension here, finite extension of number of fields is actually a simple extension. You can find something actually in F such that F is Ka, and actually I can take or K alpha, and I can actually take that alpha in fact its ring of integers T, because in general this is a fraction of two things in T, and I can take basically I can write this as a fraction of something in T over an integer as a matter of fact. And we'll say the degree of F over K is n. So let A equal R alpha. Let me point out that R alpha is a ring that's intermediate to R and T. It might be all of T, but maybe not. But the quotient field of A is the same as the quotient field of T. I'm going to let I equal the conductor ideal made of T. Let me write what I mean by this. This is a set of X in T, such that XT is contained in A. And P of prime ideal of R. Okay, yeah, these theorems are always kind of obnoxious because there's so many things I have to say. So F, so I can draw a diagram like this. And this has ring of integers T. This conductor ideal basically measures how, remember RA and T have A and T have the same quotient field. And so in fact, these two could be equal. If the conductor ideal is in fact all of T, then these are equal. And P is a prime ideal in R. The following conditions are equivalent. Let's see if I can fit them all here. Number one, PT intersect A is P adjoined with alpha. 2, A mod A intersect PT is isomorphic to T mod PT. In particular, every coset in T mod PT contains an element of A. Another way to think about this. Number 3, this is a generalization of this. If instead of intersecting it with PT, you intersect with PMT, this is isomorphic to T mod PMT. So every coset and T mod PMT contains an element of A. For every natural number M. For all M and the natural numbers, A intersect PMT is BM going to alpha. Number 5, and here's where it probably starts to get a little bit more useful. I think. Number 5, P does not divide or contain the norm of the conduction idea. And perhaps easier than that, 6, if P intersects Z, of course, P is a prime ideal in R, and these all contain the integers. And so this is a prime ideal here. We'll say generated by lowercase p, it's a non-zero prime. Then P does not divide this index. By the way, these are all finite rings, and R alpha is T. If P does not divide this inset, these are all equivalent right here. The proof of this I've written up is not terribly hard. And I'm going to publish this, and I've updated the notes to add this proof. What does this lead to? And I'll explain what the potential hazards here are. Theorem 527, and this is what I kind of waved my hands at earlier. So again, with the big setup, let F over K be a finite extension of number fields with, I want the degree of the extension to be n, I guess. Right. F of K is n with rings of integers R inside T. So same setup as we got over here. Suppose F is K adjoined with alpha and T. Just like before. And F of X and Rx, the monic irreducible polynomial for alpha. We know that alpha is algebraic, and in fact, since it's in T, it's integral over R, and so there is such a polynomial. Let P a prime ideal satisfying the equivalent conditions of theorem 526. One and hence all conditions of 526, and L equal R mod P. So L is the residue field of R mod P. Finally, let P be the map from RS. Induced by projection R mod P. So in other words, the way phi works, I think, is exactly the way you would want it to work. It takes a polynomial, all its coefficients are in R, and it maps it to whatever its residue is here. Right. Okay, so if phi of f is f1, e1, f2, e2, fk, ek, with each fi monic irreducible over L, of course. So take your polynomial here, which was the minimal polynomial for alpha, and basically take these polynomials and reduce the mod P. Factor this into distinct, that's the word I was missing. Irreducible polynomials here, powers of them. Then P up in the upstairs. Then the decomposition of the prime T basically behaves exactly like the decomposition of polynomials. Qi's distinct primes of the ring T, the larger ring T, and each degree of Fi so the degree of each of these polynomials right here, once you break down, should correspond exactly to Qi. And what is more, you can write each Qi can be written as PT, because of course each Qi contains it, plus Fi alpha T, where Fix is any polynomial. And Rx such that B of Fix is little fi. Right. That's kind of a mouthful here. Now, what you actually need is you technically need one of these conditions to hold to have this decomposition work exactly the way you want it to. For quadratic fields, this is not a problem because all you really have to do, now you're going to run into a problem in the homework. If you look, one of the problems that I asked in the homework was to consider that's the field, right? I asked you some homework about this. Its ring of integers of this F, its ring of integer T is actually Z adjoined with 1 plus radical negative 15 over 2. Right? And if this is your alpha, no problem. You don't have to worry about those previous conditions. Right? And the minimal polynomial here for alpha equals 1 plus radical negative 15 over 2 is, I guess it should be x squared minus x plus 4, something like that. Right? Now, if you just use the minus radical 15, this is the whole ring of integers, right? And so actually, this is the A listed in the statement of 526. Notice this is actually properly contained in here. And what will happen is if you try to do this theorem for the prime 2, you're going to screw up. Because actually, it's going to give you, in fact, try it. You will get a decomposition that works different if you use this extension as opposed to the full one, where you have the root of this. This will give you the correct decomposition the other ones won't. You really don't need to worry about 526 for quadratics, and more generally, for any ring of integers where you have what they call a power basis. And a power basis for the ring of integers means that a basis for the full ring of integers over the small ring can be written as 1 and x and powers of x for some fixed x. But unfortunately, not all rings of integers have this property. Just the simple small ones do. So you got to be a little bit careful. Notice that the only primes that this doesn't work for are the ones that divide and of course, this is an integer, so there's only going to be finitely many primes divided. So you're only going to have problems with finitely many primes, if any at all. And what happens if you have a problematic prime? Well, you can just adjust this alpha appropriately to deal with that, right? But for the quadratic case, if you're sagacious about what you start off with, you won't run into any problems at all. Okay. All right. Any questions on that? All right. Any questions? So hopefully you guys will have some fun with that problem. Let's go back to what we were talking about before. Grant, before I get, can I talk to you after class? Yeah. So we kind of go through this. So we have this notion of evaluation. Valuation on field is a function from K star, which I'm going to use that notation to mean K without zero. So that's a multiplicative group, K star, into G, a totally ordered abelian group that satisfies a couple of things. Number one, V of AB is V of A plus V of B for all AB in K star. And V of A plus B, it is greater than or equal to the min of VA, VB. A, B, and A plus B in K star. This is what we call evaluation, right? And we beat up a few examples about this, right? Now, so we saw some examples last time where we had value group Z. In fact, we saw some different rings that did. We talked about the p-adic valuation. You all remember where we looked at valuations on Q for every prime, did this. We looked at some other ones that were exotic as well. So let me give you this following theorem, which is a really kind of nifty theorem here. Theorem. Seven something or other, 112. Let K be a field with valuation B. Then, well, I'm going to make two statements in here. By the way, let me also point out that there's always the trivial valuation where you take every non-zero element of K to zero over in the totally equivalent group. So any field admits at least that valuation, right? So let K be a field valuation B, then number one, K is quotient field of a valuation domain corresponding to whatever this valuation B is. And number two, any valuation domain of V with quotient field K gives rise to a valuation V on K. So this is basically a correspondence theorem, right? Because what it says is, if I walk up to you on the street and I give you if I walk up to you and I give you a field valuation V, then that gives rise to a valuation domain. And on the other hand, if I have a valuation domain, that gives rise to a valuation on the field. They correspond in that nice way. And let's get under the hood and see how this one looks. Okay. So let's start off. Let's suppose we have a valuation. The suppose B A star and the G is a valuation. I want to find a valuation domain that corresponds to this value. Well, of course, I guess I could just take the whole field K, but that doesn't really correspond in a nice way. Let's let B. Any ideas on how it could sort of get, in a certain sense, an interesting valuation domain out of this map?
Take the elements with non-negative value.
Okay. And of course, I want this to be the ring. Let's throw in 0 as well. And we're gonna need 0. So B is the set of everything. So take this valuation. It's giving you the thing. G is a totally ordered abelian group. So if you have anything in G, it's comparable to 0. It's either greater than or equal to 0, or it's less than 0. So take this map and just pull out everything that has valuation 0 or greater. Throw in 0 for good measure, and I claim that this is a valuation domain. First, I guess I better claim that it's a ring. Certainly it's a domain because it's a subring field if it is a ring. Notice that for all A, B, and B, value either A plus B equals 0, in which case it's in there, or the value of A plus B is greater than or equal to the min value of A, value of B, which is greater than or equal to the B value. I guess I better be careful here. Let's take A, B, be non-zero. Then either they add up to 0, in which case they're in B, or the value of the sum is greater than or equal to the minimum. Since they're both non-negative, it's in there. So A plus B is in B because its total value, it's either 0 or its total value is greater than or equal to 0. If either A or B is 0, then it's still okay. Because 0 plus 0 is 0, which is in there, and 0 plus A is A, and so we're good to get there. Am I okay with that? Number 2, I need to be closed under multiplication. Let A, B, and V. If A or B is 0, then done. Because 0 times anything is 0, which we've defined to be in the domain. If not, the value of AB is value of A plus value of B, which is greater than or equal to 0. And there we go. So this set is closed under addition and multiplication. It inherits all the rest of the stuff. So this is in fact an integral domain. Now, the question is, why is it a valuation domain? And so, why is it?
Take any, I guess you could go with either definition, take any two elements, look at the greater one divided by the lesser one. And the quotations.
Right, you're right, I see, I'm gonna go, and so if omega is in K, but not zero, then consider the value of omega. If the value of omega is greater than or equal to zero, then we're good to go, it's in there. If not, then it's less than zero. Because remember, the value lands in a totally ordered group, so the value of omega is either greater than or equal to zero or strictly less than zero. If it's less than zero, then minus. So it's valuation domain. Because for any omega, it's either in there or it's inverse. Okay. Questions on? I think the other direction is more interesting because you got to think about the groups. So what we've shown is if I walk up to you on the street and I give you a value on a field, then bang, you've got, just by considering the non-negative elements zero value, you get a valuation domain. What if I give you a valuation domain? Valuation domain with quotient field. I would think now, of course, you could be a smart aleck and say, well, Jim, just take zero, right? Take the function that takes every non-zero element of K to zero element here. But that doesn't really reflect what I want, because really I want to sort of recapture what I have here. I want the stuff to be in the valuation domain if it's got a non-negative value, and not in the valuation domain if it's got a negative value. The big question here, I think, is what is G? What is the choice? How should we select G?
Well, any two elements of B are comparable, so that's kind of a bordering. That's good.
Okay, good. So let's let. I'm not even quite sure if thusly is a word, but I'm going to boldly use it. Let's let G equal the non-zero elements of K modulo the units of V. And this is notice I'm used to my valuation groups being, or my valuation or my totally ordered group being written positively. I apologize for this. I'm going to write this multiplicatively because this is very naturally a multiplicative group. So I've taken the zero elements of the field as a group under multiplication, and I mod out by the units of V. So for example, of course, Z is not a valuation domain, but you can do this for any other domain. This is actually called the group divisibility. And you can do this actually for any integral domain, just by taking an integral domain, take its quotient field, take the non-zero elements and mod out by the units of the domain. So for example, if you have the ordinary integers, right, take the rational numbers, kick out zero, and mod by the units of the integers. And the units of the integers are plus or minus one. So the group of divisibility for the integers is just the positive rationals under multiplication, right? And actually, in a certain sense, that kind of measures it, because the positive rationals under multiplication are generated by the primes, right? Right, because any positive rational is a product of primes, if I'm also allowing negative powers as well, right? But this one, well, okay, it's gotta be totally ordered, so I need a partial ordering at least. So I think you hit on it at the moment. Yeah, what should the condition should be? Let me convince you why this works, right? Because nobody was shouting out answers, so let's see if we can convince ourselves. First, I need to convince myself it's a partial ordering, then I'll show it's in fact a total order, a total ordering. Let's see, what do I need for a partial ordering? Let's see, I need reflexivity. I always get that one confused a little bit. Notice that K1 over K1 equals 1 in V. So K1 UV is less than or equal to K1 UV, right? I'm gonna go straight, so we've got that. Right, so that's one of the things I need to part of it. I'm gonna go for transitivity next. Suppose that K1 UV less than or equal to K2 UV. And K2 UV is less than or equal to K3 UV. First condition means that K2 over K1 is in V. Second condition means K3 over K2 is in V. And I don't know much, but I know that V is an integral domain, so in particular it's a ring. So the product of these two things are still in V. So therefore, UV less than or equal to K3 UV. Okay, so it's transitive, right? And we need what's it called antisymmetry, right? We need it to be antisymmetric. So we need, suppose that I'm trying to do this, so we'll say XUV is less than or equal to YUV. And suppose we've got this going on. Well, notice that this means that Y over X and also X over Y are in the units of V. Or I'm sorry, are in V. Full surprise. These are both in V, right? So Bill and Bill inverse are both in V. So Bill is a unit in V. So Y over X is in the units of V. Right? Therefore, there's my anti-symmetry. Everybody okay? By the way, where in this did I use the fact that V was a valuation domain? You were right not to answer because I didn't, right? This doesn't, so far, none of this is dependent on it being a valuation domain. That's why you can do a group divisibility in a more general sense. Everybody okay with that? Okay, so this is what we're going to do. We're going to let G be this. And my value, so this is, oh, wait a minute. I get so excited that sometimes I forget that I have proved everything. Oh, which has gotten me into trouble before. Okay, I also need it's a totally ordered billion group. This is where valuation domain is going to come in. Because the group of divisibility, in fact, you can prove very easily, as a matter of fact, that the group of divisibility, this general construction, is totally ordered as a billion group, if and only if the domain was valuation domain. So we need to show this thing's totally ordered here. So let XUV and YUV be in this monster here. Well, I need to show that, of course, X and Y are in V. Then Y over X is in V, or X over Y is in or both. Right? This, of course, is the key step where we're using the fact that this is valuation domain, right? One of these quotients has to be in V. Translation of this, either XUV is less centered than YUV, or YUV is less centered than XUV. So if V is a valuation domain, K star mod UV is totally ordered. Okay, questions on that? Now, I've got a little ways into this. But what I need to do now is show that I can make a valuation out of this. So we're going to do, because this is a math class, we're going to do the easy thing. We're going to we now define B from K star to, now that I know what my value group is, this is more or less an inspiration of what to do. V of X is X UV. Now, in my proof now that this is actually an honest to goodness valuation, I am going to keep in mind that my group, my totally ordered group here on the right side is actually written multiplicatively. So I'm going to have to use multiplication instead of product here. So the first thing I have to do is, number one, let's do this. Well, what is this? This is AB UV, which is AUV. This is the easy part. B UV, which is value of A, value of B. Right? Not a plus, but a times, right? Because that's the operation of all three. Right, okay with that? Okay. The more interesting part is to suppose A, B, and AB are not zero. And let's look at the value of A plus B. Now, of course, my end game is I want to show that this is greater than or equal to the value of the minimum. Right. So, any ideas on how to do that?
Pick out which one is the minimum and sort of factor it out.
Okay, good, good. Without loss of general, well, so what do I know here? This valuation domain. In V, A divides B or B divides A. Without loss of generality, suppose A divides B. Okay. So if you look at the value look at the value of A plus B. This is the value of A times 1 plus B over A. And notice that 1 plus B over A is in B. Now, I've already seen that this is the value of A, value of 1 plus B over A. Right? And this is greater than or equal to the value of A. Right? And the reason is, notice that so for this last step, notice that right, that quotient is in B because when you cancel the A's, this thing we've established is in B. And so by definition, this means that the value that's the total ordering we had on the group, right? And so, hence, value of A plus B is greater than or equal to min value of A, value of B. Because we selected A to be the minimum value anyway. Are you okay with it? And let me point out that under B, the non-negative, well, let me say the elements of K of non-negative value are precisely the non-zero elements. And that is why valuation domains are called what they are, because they come from this function valuation. So given this valuation, we have valuation domain, given a valuation domain, we build a valuation. So that's where the strange A divides B or B divides A leads to this function. that's good for today. Next time, I've sort of beat valuation domains to death. We're going to talk about how to globalize them. And we're going to look at proofer domains, and Dedekind domains. Proofer domains are sort of globalizations of valuation domains in the sense that, locally they're valuation domains. Dedekind domains are proofer domains that are in Ethereum. So, okay, any questions? All right, well, consider Neil's talk today, and otherwise, y'all have a very good evening. We'll see you on Monday.